SwayamPrabha. Digital India. Educated India.
Good morning everyone. Today we will start solution of Navier-Stokes equations for incompressible flows using MAC algorithm. I have already explained MAC stands for marker and cell, and this algorithm was developed in the Los Alamos National Laboratory of the United States, primarily by the research group of Professor Harlow and Professor Welch, and the version which we will study here is called sometimes simplified MAC method, and this was developed by Professor Hirt and Professor Cook in 1972. Now, this algorithm is widely used and quite easy to learn and implement it for solving the problems that we usually face in our research parlance or for solving industrial problems. Now, this uses unsteady Navier-Stokes equations for incompressible flows, and we use weak conservative form and continuity equation. Description of the problem is elliptic in space and parabolic in time. Solution is marched in the time direction. At each time step, a converged solution in space is obtained, but this converged solution at a time step may not be the final solution of the physical problem. If the problem is steady in its physical sense, then after a finite number of steps in time direction, two consecutive time steps will produce identical solutions. However, in a machine computation, this is not possible because numbers everywhere, every location between two time steps exactly same up to maybe 16 decimal place or 10 decimal place or sometimes 20th decimal place. It is not possible. So there will be a small difference even if it is converged. So that is why we specify a very small number as the upper bound. Let us call it a variable stat. Specifically, stat may be chosen between 10 to the power minus 3 and 10 to the power minus 5. That is good enough if the maximum discrepancy of any of the velocity components for two consecutive time steps at any location over the entire space does not exceed stat, then it can be said that the steady solution has evolved. That means at each locations, whatever values we get, at the same locations, the values that we get in the subsequent time step, they are same. And if there is any difference, that difference is less than, say, a predefined value, which may be 10 to the power minus 4 or 10 to the power minus 5. If the physical problem is basically unsteady in nature, the aforesaid maximum discrepancy of any dependent variable for two consecutive time steps will never be less than stat. So it will keep on varying the difference. However, for such a situation, a specified velocity component can be stored over a long duration of time, and plot of such velocity component against time will give us lot of important information. These are often such storage of velocity over time is called signal. So and the signals are very useful in determining the different characteristics of flow, whether it is unsteady periodic or unsteady chaotic, or it's transitional flow. All such things can be depicted very nicely from such signals, which are basically collection of velocity components at specified locations over time. Now, but at this stage, let us call it when this maximum discrepancy of velocity at any time location is not falling below a specified predefined small value, then the flow is oscillating. It's basically, we can call such flows as unsteady flows. Then with the help of momentum equations, we compute explicitly a provisional value of the velocity components for each time step, and then from that provisional value we get the real value or the converged value or final value for that particular time step. Now, when we discuss about the flow equations, obviously the first equation that comes, continuity equation. Then let us take up x momentum equation, and as you can see, we have taken x momentum equation in weak conservative form. Del u del t del x of u square plus del y of uv plus del z of uw equal to minus del p del x plus 1 by re del square u, which means del 2u del x2 del 2u del y2 del 2u del c2. It is assumed that at time t equal to nth level we have a converged solution. This can be initial solution also, or initial values can be used in such a way that that can be considered as the nth level solution. Then the next time step, so basically we progress from n to n plus 1 to n plus 2, so on and so forth. So when we have converged value of the velocity field and the pressure field, we have the converged values everywhere at nth level. From there, for the next time step, we can write for u component of velocity, we have started with x momentum equation. So obviously u component of velocity uijk at a point ijk at the next time level, that is n plus 1, and we have used another sign tilde because there is a reason. This is not really n plus 1, as I said, it's provisional value. Therefore, to identify its provisional state, we have used this tilde value. So this is equal to uijk at nth level plus delta t into condiff, which is convection diffusion part of u velocity minus dp dx. Just the way it is written there, you can see we have just numerically transferred those values. Del u del t means u at n plus 1 minus u at n by delta t. So u at n plus 1 then will be u at n plus delta t. If we transfer all these components on the other side, delta t multiplied by all these terms. Now among these terms, these first three terms are convective terms, and terms associated with 1 by RE are diffusive terms. So delta t into convective and diffusive terms of u momentum equation, that is why you have written condiff u minus del p del x. All these values are evaluated at ijk point at a time level n, at nth level. Those multiplied by t plus uijk at nth level is uijk at n plus 1th level provisional. Basically del u del t is uijk at n plus 1 minus uijk at n by delta t equal to all these terms which we are calling as condiff u and dp dx. So uijk at n plus 1 is basically then delta t into all these terms plus uijk at n. And as I said, that when we write this way, or when we calculate this way, this velocity is projected velocity at n plus 1th level, but not really the final velocity at the level n plus 1. Why, I will explain shortly. And since this is provisionally calculated, not converged as yet, we'll call this u as provisional u, and that is why together with n plus 1 we will use this tilde. So this is equation 2. Here we have explained condiff u minus dp dx at point ijk at the level n consists of convective and diffusive terms and the pressure gradient. Similarly, the provisional values of vijk at the level n plus 1 tilde provisional and wij at the level n plus 1 again provisional tilde can be explicitly computed. I'll go back by one slide. So those u momentum equations can be casted in this mold, and w momentum equation can be also formatted in this way to calculate the provisionally advanced v velocity and w velocity the way we have calculated provisionally advanced u velocity. These explicitly advanced velocity components may not constitute a realistic flow field. A divergence-free velocity field has to exist in order to describe a plausible incompressible flow situation. Now, with this provisional value of U, V and W, continuity equation is evaluated in each cell. If so, continuity equation, divergence of V, this V is vector V signifying U, V and W, all three components. So if divergence of V produces a non-zero value, there must be some amount of mass accumulation or annihilation in each cell, which is not physically possible. So this, why we are calling these velocities as provisionally advanced U or provisionally advanced V or provisionally advanced W, because we do not know whether they satisfy continuity equation. And we'll see indeed they do not. After this provisional advancement, they do not really satisfy continuity equation. So non-zero continuity means mass annihilation or mass accumulation, which is not possible. So we have to reach a situation when divergence of V equal to 0, then only these provisional velocities will be the velocities at the level n plus 1. Therefore, the pressure at any cell is directly linked with the value of divergence V of that cell. Since divergence is not satisfied, you cannot accept pressure of that cell as converged pressure or the final pressure. Now, on one hand, pressure has to be calculated with the help of non-zero divergence value, and on the other, the velocity components have to be adjusted. The correction procedure continue through an iterative cycle until the divergence-free velocity field is ensured. Detailed calculation we will be acquainted with slightly later, how to go about that. Now I have to mention about boundary conditions too. So boundary conditions are to be applied after each explicit evaluation of the time step. So when you go from one time step to another, obviously we have to apply boundary conditions on all confining surfaces. Since the governing equations are elliptic in space, boundary conditions on all confining surfaces are required. Moreover, the boundary conditions are to be applied after every pressure velocity iteration. Not only after advancing from one time step to the next time step, but when we calculate, I have mentioned, we have to correct velocity and we have to correct pressure, and this is an iterative process, and for every iteration we have to apply the boundary conditions, because boundary conditions are to be satisfied for a converged flow field. So we will discuss 5 types of boundary conditions: rigid no slip walls, free slip walls, inflow plane, outflow boundaries, and the periodic boundaries. We will specifically discuss all this. The region in which computations are to be performed is divided into a set of small cells having edge lengths delta x, delta y, and delta z. Shown in this figure, you can see that this delta x's form the length, so it extends from I equal to 1 to I equal to maximum value IIM. The last but one cell is called IIRE. Here also the second cell is I equal to 2. Why this IRE has been specifically used, we will discuss little later. So in the x direction, which covers L dimension, we go from I equal to 1 to IIM. Similarly, in the Y direction, we go from J equal to 1 to JIM, maximum number of cells. And in the Z direction, that is varies with K direction, we go from K equal to 1 to KIM. And each small segment in Z direction is delta Z. Each small segment, or the width, cell width in Y direction is delta Y, and X direction is delta X. So this is how we discretize a domain. The region in which computations are to be performed divided into a set of small cells having edge lengths delta X, delta Y, and delta Z. We have already seen that. With respect to this set of computational cells, velocity components are located at the center of the cell faces to which they are normal. I have already mentioned about staggered grid and the location of the variables. So let me repeat it again. Velocity components are located at the center of the cell faces to which they are normal, and pressure and temperature are identified at the center of the cells. Cells are labeled with an index IJK, which denotes the cell number as counted from the origin in the X, Y, and Z directions. So from the origin in the X, Y, and Z direction, we make progress by delta X, delta Y, delta Z, and cover the full domain. Basically, which cells are labeled with an index IJK, which denotes the cell number as counted from the origin in the X, Y, and Z directions respectively. Also, Pijk is the pressure at the center of the cell IJK, while Uijk is the X direction velocity at the center of the cell face between the cells IJK and I plus 1 JK, which is explained in this figure. See, this is the central cell 1. We can call this as IJK cell. And at the center of the cell, we can see that Pijk has been defined. We'll also calculate later temperature. That is why theta ijk has also been defined at the center of the cell. So this is IJK cell, and this eastern neighbor is I plus 1 JK cell, three-dimensional cell. And what we have said here, that Uijk in the X direction velocity at the center of the cell face between the cells IJK and I plus 1 JK. So this is IJK cell, this is I plus 1 JK cell. Between these two cells, this is a cell wall, and at the center Uijk has been defined. Similarly, look at this cell IJK, and this is IJ plus 1K cell. So between these two cells, at the center on the cell face of IJK, at the center Vijk has been defined. So this is how the velocities and the pressures are located on the grid mesh. Because of the staggered grid arrangements, the velocities are not defined at the nodal points, but whenever required, they are to be found by interpolation. So velocity, pressure, they are located in specific location, but if somewhere it is needed but it is not defined, then those are to be interpolated. Like, for example, here center of the cell Vijk is defined. Here also center of this cell Vi plus 1 Jk has been defined. Now on this line, at center of this line, if we want to find out Vijk, or if we want to identify V value here, then that V value will be basically Vijk plus Vi plus 1 Jk by 2. These two will be interpolated at this point. Similarly, Uijk is defined here, Ui minus 1 Jk is defined here. But at the center of the cell, U is not defined. P is defined, theta is defined, but not U. So if we need at the center of the cell U, then that will be Uijk plus Ui minus 1 Jk by 2. Here it is linear interpolation, and as I said, that appropriate interpolation has to be done at the point where the velocity is not directly defined. Velocities are defined at specified locations. So that is what we have said here. Where a product or square of such a quantity appears, it is to be averaged first, and then product is to be formed. Since we have used uniform grid, we have written averaged. Otherwise, we can also use the word interpolated. So basically, where it is not defined, there it is to be defined either through interpolation or averaging, and then product is to be formed. Convective terms are discretized using a weighted average of second upwind and space-centered scheme. This is a central difference scheme and second upwind scheme. Average of that, which is available, as I have mentioned. This work was done by Cyril Hirt. So in his work, I will discuss this. And diffusive terms are discretized by a central difference scheme. So this is, now we will give an example how U momentum equation is discretized or X momentum equation is discretized. So this is three-dimensional grid has been drawn, and if we see first term of X momentum equation, convective term, first term is temporal term del U del T, but in the among the convective terms, first term is del X. It is conservative form. First term is del X of U square. So simply it has to be defined where Uijk is defined at this point. So at this point, if we have to find out del X of U square, we can write central difference, and that will be U somewhere here, which is center between these two U's, minus U somewhere here, which is at centrally located between Uijk and Ui minus 1 Jk somewhere here. So this U, which is not shown here, but average of Uijk plus Ui plus 1 Jk square. So basically U square, we have to write del X of central difference. That means U at this location square, U at central of the center of the cell square divided by delta x. So 1 by delta x. Now this u means uijk plus ui plus 1 jk by 2 square, and this u, which is between uijk and ui minus 1 jk, is ui minus 1 jk plus uijk by 2 squared. So this, just simple algebra, 4 will come out, 1 by 4 delta x, and then we can write uijk plus ui plus 1 jk again into uijk plus ui plus 1 jk. Just we have done little in detail this calculation. ui minus 1 jk plus uijk, so ui minus 1 jk plus uijk into ui minus 1 jk plus uijk. So we have just expanded these two terms, and then what we have done, we have applied upwinding. And for applying upwinding, otherwise this is central difference. We have expanded this up to this, it is central difference. Upwinding has been done here. As you can see, we have brought this uijk plus ui plus 1 jk under modulus sign, and then multiplied with uijk minus ui plus 1 jk. And we have also multiplied this quantity which is under modulus sign with alpha. This represents basically these two terms, and the terms which are subtracted, they are represented this way: ui minus 1 jk plus uijk into ui minus 1 jk plus uijk minus alpha, again ui minus 1 jk plus uijk. These two terms together are brought under modulus sign, and then ui minus 1 jk minus uijk. Now if you look at this discretization, if you set alpha equal to 0, it will remain central difference. If you set alpha equal to non-zero value, then upwinding effect will start coming. But if you set alpha equal to 1, then it will be full upwinded, first order upwinding. And this sign is under modulus sign. This terms uijk plus ui plus 1 jk, this quantity is under modulus sign in order to give the flexibility, because locally in a flow field it is quite natural that there will be some obstructions, there will be some undulations, and there may be flow separation. If there is any flow separation, then there will be locally negative velocity. So this, we have given that flexibility, that this uijk plus ui plus 1 jk, we have put it under modulus sign. That means this will remain valid whether that velocity is positive or negative. Similarly, we have also used modulus sign for ui minus 1 jk and uijk. That means u at the center of this cell. So that velocity locally may be negative or positive depending on its location. If it is located after the point of separation, u velocity can be negative there, and otherwise it is positive. So positive or negative, to play with both, we have applied modulus sign here. So that is what, and if you recall, we have already discussed this way of discretizing the finite difference quotients in our first probably first lecture or second lecture, where we discussed about basically the forward difference, backward difference, and then we wrote the full form probably in seventh lecture, where we introduced formally several appointing methods and higher order appointing. Now, so this is what we have done, and we are writing this discretized form again and giving it a variable name. We are calling it, we are defining this as duu dx, simply ddx of u square. So we are, as if this variable is a variable in a program, so you have given a name following that sequence in a code. This is being defined as duu dx, and this is exactly the same term that we have written here, del del x of u square. So we can look at it. Alpha is there, and ui jk plus ui plus 1 jk, that means between these two, u by 2 is obviously hidden, has come here, and that velocity under modulus sign, and also ui minus 1 jk and ui plus 1 jk, average of that velocity. That means at the cell center, whatever is the velocity, u velocity, is under modulus sign. And we are using alpha, which we are calling as basically the appointing contribution, or contribution appoint factor, right? Usually this should be a small value. We will come to that again. Then we have gone for the second term, del del y of uv. Now see, when we find out del del y of uv, we have already mentioned how to do that. Here also we will apply central difference, but this del del y of uv, that has to be defined where uijk has been defined. So if we have to define at the point of uijk, then we have to define u into v at this point, and also u into v at this point. Then u into v at this point minus u into v at this point divided by delta y, we will give del y of uv here. So terms associated with x momentum equation, we have to determine all the quantities at a point where uijk has been defined. So the second term of the momentum equation, del y of uv, we have to calculate at this point where uijk has been defined. So we have to find out u into v at this location and u into v at this location. We have exactly done that 1 by delta y. And this first term, that means del into u is at this location, will be vijk plus vi plus 1 jk by 2 multiplied by uijk plus uij plus 1k by 2. So that makes us available u into v at this point. that makes available this term. Now again u into v at this point, that means vi j minus 1k is defined here. Vi plus 1 j minus 1k is defined here. So average of these two terms, vi j minus 1k, this term, vi plus 1 j minus 1k by 2, and u will be uijk plus uij minus 1k by 2. So uij minus 1k plus uijk by 2. So simply we have found out by interpolating u at this point. Between these 2 points we have interpolated, sorry, it has come here. Between these 2 points we have to interpolate u. So we have done that. Between these 2 points again we have to interpolate v here, and using these 2 points we have to interpolate u here. So u into v at this point is this quantity, and u into v at this point is basically this quantity. So 4 comes out, and then we get these terms. Again we go for upwinding, and the factor is contribution of upwind factor is alpha, and we make this locally this v plus this v, that means v here, and this v plus this v by 2. So these two v's locally we have added flexibility on these two views, so that expression can be independent of these two v's, whether they are positive or negative will not affect the discretization. The discretization will assume the correct form of upwinding. So u at u at this point, that means u ijk plus ui plus 1 jk by 2, that means u ijk plus ui plus 1 jk, this quantity under mod, and also vi j minus 1k and vi plus 1 j minus 1k, vi plus 1 j minus 1k and vi j minus 1k, average of these two v's here also under a modulus sign to create the flexibility that it can be positive or negative both. So we have again just written those terms, and we are calling it as d uv dy. This is del y of uv. We have rewritten basically the previous slide, and the final result of this slide are same. Basically we are evaluating or discretizing del y of uv and assigning it a variable name duv dy. So duv dy, that is how we have done. Similarly, the third term of x momentum equation is del z of uw. I am not explaining it. We have explained first two terms. If you follow the way first two terms have been handled, third term will also be handled in a similar way. We have to write the expression first in central differencing. Then we have to create provision for upwinding, and then we have to make the local velocity. We have to consider local velocity can be positive or negative, and make the expression or the discretized form independent of that by using modulus sign. And we will call this as duw dz. Then del p del x, we have written pi plus 1 jk minus pi jk by delta x. Simply del p del x, we are calling it, we are assigning this variable name dp dx. Now the diffusive terms, condiff u, we called the total term. So diffusion terms are del 2u del x2, del 2u del y2 and del 2u del z2 at the point where uijk has been defined. So again, if we go back by one or two slides, so we have to, since it is associated with u momentum equation or x momentum equation, where uijk has been defined, here we have to find out final difference quotient of del 2u del x2, del 2u del y2, del 2u del z2. Del 2u del x2 will be ui plus 1 jk minus twice ui jk plus ui minus 1 jk divided by delta x square. So we can see ui plus 1 jk minus twice ui jk plus ui minus 1 jk by delta x square. Similarly, del 2u del y2, if I'm again going back by few slides, so we have to make use of this ui j plus 1k minus then twice ui jk plus ui j minus 1k divided by delta y square. So ui j plus 1k minus twice ui jk plus ui j minus 1k by delta x square. Similarly, in z direction, if we find out the second derivative of u at the point ui jk, we will get this quotient, and we will define this as a variable which will be used in computing. This is simply, we have written d2u dx2, d2u dy2. The variable name is taken from directly the terminology. The del 2u del z2 is d2u dz2. And as we have said, that all these discretized equations are containing alpha. Alpha is the upwind contribution, and alpha equal to 1, it is second upwind. Alpha equal to 0, it is central differencing scheme. We will not use purely central difference scheme because we have seen this may give or produce instability, numerical instability. So we will, for the stable calculation, we will introduce upwinding, but this alpha value will be a very small value. A typical alpha is between 0.2 and 0.3. The quantity uijk n plus 1 tilde is evaluated explicitly from the discretized equation 2. We mentioned about it earlier, that is uijk tilde at n plus 1 is uijk n plus delta t into condiff u. We know all the components of condiff u now, minus dp dx at ijk point at nth level, and components of condiff u are we have evaluated them one by one. Du dx, then du dy, du v dy, du w dz, dp dx, d2u dx2, etc. But when we transfer the governing equation, when we transfer first three terms on the right hand side, all of them will have negative sign. So in condiff u, when when we are writing du dx, that means d dx of u square, that is with negative sign, d dy of uv, d uv dy with negative sign, d uw dz with negative sign, minus dp dx, and diffusive terms will be without any change in side, as a change in sign. They are not changing side also, no change in sign. So plus 1 by Re into all the diffusive terms. So this way, if we can calculate condiff u minus dp dx at nth level at the point ijk, and if we add it with u velocity at nth level, after multiplying by the time step, we will get provisionally advanced value of uijk at the level of n plus 1. And since it is provisionally advanced value, we are also using tilde sign. So this is the way provisionally at every point u velocity is advanced. Similarly, provisionally at every point v velocity can be advanced and w velocity can be advanced. And they will follow same convective kinematics and diffusive laws and the effect of pressure gradient. Instead of condiff u, this will be condiff v, convective and diffusive terms of v momentum equation, dp dy instead of dp dx. In v momentum equation, it will be dp dy. And in w momentum equation or z momentum equation, it will be condiff w minus dp dz. And we will get provisionally advanced u at every point, provisionally advanced v at every point, provisionally advanced w at every point. And this is the discretized form. Discretization has been done. U for the terms associated with x momentum, where uijk has been defined. Similarly, terms which are associated with y momentum equation, all those terms will be determined where vijk is located, and the w momentum equation or z momentum equation, all the terms will be evaluated at the point where wij has been defined. We'll stop here today. Remaining parts will take up in subsequent lectures. Thank you very much. Thank you.